Hi everyone. So today we're diving into something really cool, which is fine-tuning YOLO models for soccer detection. We're going to detect balls, referees, players, goalkeepers um, in a soccer match. So we are going to use the Ultralytics fine-tuning tools. And but let's see what we are working with. So the popular YOLO models, like the models we've already seen, like YOLO Ultralytics, YOLO V8, V11, now with V12, with different sizes, and also YOLO X. They're mostly all pre-trained on something called the COCO dataset. So what's COCO? It's a massive dataset that contains 80 different object classes, things like a person, bicycle, car, dog, a cat, even kites. Everyday objects you see around. And honestly, these models work incredibly well for generic scenarios. And if you're trying to detect people, cars on a street, they're a fantastic right off the box. But here is where it gets interesting. And this is the real magic of these pre-trained models and pre-trained models in general in most of the cases. So they're not just good as detecting those 80 classes. They're actually amazing as a foundation, as a starting point that we can build upon. We can take these models and fine-tune them on our specific dataset to make them specialists in whatever domain we care about. So now you might be thinking, why not just train a model from scratch, for example? The thing is, training from scratch is, especially like a YOLO model, it's a tough road. And training from scratch means that we need first an absolutely massive data set, like for example a COCO data set. It takes thousand of images per class that are perfectly labeled, and then we need a serious compute power to train the model. And then after all this work, the final accuracy most of the time is lower than the fine-tuned model. And the reason is because the pre-trained models have already learned the fundamental visual features. They understand edges, shapes, textures, patterns. All knowledge is compressed and encoded in their weights. So when we fine tune, we are not starting from zero. We're building on the top of all these learnings. So here's what we are going to do today, and we are going to fine-tune a pre-trained Ultralytics YOLO model, pre-trained on the COCO dataset, and just focus on four classes: ball, goalkeeper, player, and referee. So yeah, goalkeeper, player, referee, they're all people. So we could just use the YOLO model, the pre-trained model, pre-trained on the COCO dataset, since it detects people really well, which is a good point. But the reason why fine-tuning is worth it is that we want our model to be a soccer specialist. We want it to excel at detecting players in motion, goalkeepers diving, referees in their uniforms, and ball that might be partially hidden by the player's feet, for example. So all these objects and people are in specific contexts of the soccer field. So fine-tuning teaches our model these soccer-specific details that a generic model just can't handle as well. So we're going from a generic 80 classes detector to a specialized 4 classes soccer detection system. that's laser focused on what actually matters in a match. So let's dive in. So we start from data, and so since we are fine-tuning the model, we don't need as much data as starting and training a model from scratch. But still, we need a few thousand of images, and we're looking to have around 10,000 images, between 5 and 10,000 images. What we are going to use is like, for example, this website, which is RoboFlow Universe, and it's great to look for open source data sets, and there are many. You see here: license plate recognition, people detection, and here I found a soccer data set. So first, under overview, you see the classes. So this is perfect for object detection. There are other data sets that are that have labeled data, like for segmentation or classification. But here, this is great for our what we want to do. And so you see here some example. So if we go here under images, you can see that player, ball, player, and here we see some other examples. This is the ball, players. Okay, let's see if we find, yeah, you see here referee, and there should be a ball. Okay, so here we have around 9,000 images. Here we see that we have the images are split in 3 sets. So the main one is the train set. These are the images that are going to train the model. These images are fed into the model, and so what are validation set and test set? So validation set is super important. Is the set we use during training to understand if the model is generalizing. Generalizing means that we are using these images to train the model. We need other images to understand, so different images. So the model hasn't seen these images, and we need these images to see if the model is detecting the objects correctly in these images. So what has learned here, we need to understand if the model generalizes the learning and is able to understand where the objects are in these images. And at the end, we use the test set to see to have like a final accuracy, understand the final accuracy of the model. We can download this, and we see that there are many formats. The main two are YOLO v11 and CocoJSON, the 2 main formats, but we are going to use YOLO v11 because we are fine-tuning Ultralytics YOLO v11. Great, and you can download the zip here, and let's see what is inside the zip file. So we have data, YAML, and then 3 folders. Each folder has another 2 folders, images and labels. Inside images, we have the images with different sizes. So you see here this. Okay, and inside labels we have TXT files. So for each image we have a TXT file with the same name, and inside the TXT file we have, you see these lines, and each line is for each object. So I have a good example here. For example, here we have players, goalkeepers, and referees. And here we have the TXT file. So remember, so here we have inside data YAML, we have the class names, the number of classes, and the where each set is. And usually the ball, in this case, the first class is, the index is 0. This is 1, this is 2, this is 3. So if we go inside here, you see 2, 1, 2, 2, 2, 3, meaning player, this should be player, right? Yeah, player, 1 is goalkeeper, and 3 is referee. So player, goalkeeper, player, referee, player, ball, and referee. So, okay, this is the class, and this is the bounding box. You see, it's a float, meaning it's relative to the width and to the height of the image, meaning 80% from the left. This is the center of the bounding box. So 80% from the left, 30% from the top. And this is the width. This image, so the objects are pretty small inside this image. So you see here that the width is basically 1% of the full width of the image, and this is 2% of the full height of the image. So let's try to see where the ball is. It's 80%, around 80% from the left, 30% from the top, and it's really small. So 80%, yeah, 80% from the left and 30% from the top. Okay, yeah, 80 is here. And you see that it's actually here. It's actually here. So we see that, for example, the referee is here, and the goalkeeper is here. Let's see, the goalkeeper is 1. So 2% from the left, 43% from the top, 2% from the left, yeah, around 40% from the top. So this is how the label file works. And the Ultralytics tooling is going to load all these details and start training the model. Okay, I've downloaded and unzipped the file. So we see here the data YAML. It's the same. Is the same I shown you in the with the Visual Studio Code. So we are going to use the Ultralytics tooling, which is a Python library. So here I'm on my MacBook Air. So Python 3, I think version 3.10, but it shouldn't matter which version. I mean 3, but 3.10, 3.11 is fine. They're fine. So we're going to use the virtual environment. So we're going to create a virtual environment. So we see here, we load the virtual environment. And we install Ultralytics. This library is also used, obviously, to run the YOLO models, not just train. We have everything inside here. Okay, and now it's simple. We see that in the virtual environment, we have a bin, and the bin, you see here that we have TensorBoard, okay, but we have YOLO. So this bin folder is already in our path, and so we can use YOLO here. Okay, so here there are many things we can do, but what we are going to do is to train. Okay, so we're going to run YOLO train data. This is the data YAML file we have of our dataset that describes where the images are, number of classes, and the name of the classes. YAML. And then the model, this is the model we want to fine-tune. So YOLO 11N, that's for nano, is the smallest PT. It's going to download this automatically. And then the number of epochs. So epochs is the number of time we go through the whole training set during training. So 50 means 50 times. So because usually we don't just go through one time. And this really depends by the kind of model we trained and the amount of data we have. This is one of the parameters of training. And in this case, for this kind of model, I've seen that 50, it's okay. Maybe we see this a little bit better later, but you can see the documentation of what exactly this is. One way of describing the epochs is like reading and reading the same book over and over. The first time you see certain things, the second time you read the same book, it's not just the same experience. It's a different experience because you're different. It's the same for when training a model. When after the first epoch, the model learned a little bit with the first set of going through the first time, going through the training set. And the second time will be different. The third time we update again the model, and it gets better and better and better. And image size 640. This is the input image. It's 640 by 640. Great. Okay, so we see that it downloads the model automatically. Here we see that it's using the CPU here on my MacBook here. It's an M3, and we will see it will go quite slow. So this is, if you're interested, I'm not going into much detail, but this is the neural network, the convolutional neural network. The number of parameters, it's remember this is the nano version, 2.5 million of layers, 2.5 million parameters, 181 layers. Usually when they're what is called fusion, it's an optimization. This should go should be around 70, 80. Maybe we'll see this later. But yeah, and then it starts the training. So this is the first epoch, and you see that we're just at 3%. And the first epoch is going to last on this machine around 30 minutes, and 50 epochs is going to take forever. Probably there is some optimization for this machine, but it's not the point. What I want to show here is that if you have a machine like this, like mine, is take, you can try to find a way to accelerate this on this machine. Probably it's possible to some version, I don't know, and please let me know. If you want to run this training with this library version on a machine like this, you're going to wait a lot, or you just pick not just 50 epochs, but you choose something like 6 epochs, 8 epochs, and you will wait, around a few hours, and you will see something that's probably decent after 8 epochs. But what I will do is to use a machine with the GPU. So I'm going to stop this. So I'm going to use a box, a Linux box. This is Ubuntu with the GPU, which is an NVIDIA L40S. So I want to thank Glisses. Glisses, it's a Swedish data center provider that let me borrow this machine with GPU, as they wanted someone to help evaluating this as it rolls out for general availability. And as we can see, this GPU is pretty good. It's we have 46 megabytes. 46 gigabytes of RAM. Let's see if we can find exactly which is. It's an NVIDIA L40S. Great. Okay, let's start the training again here.
So the big difference here is the number of parameters. It's around 20 million here, and the number of layers. So more layers, more parameters, and yeah, probably each for sure each layer has more parameters as well. So it's definitely a larger model. So the cool thing is that it's going much faster. And the first epoch is almost, so here you see the GPU memory it takes during training, and the first epoch is almost done. So there are two things we need to see and to check during training. Well, the first one is loss. So here you see there are three numbers, and all three are losses, because we have three different losses in for this model. So there is box loss, class loss, and this is the focal loss. So the important thing about loss in general during training is that we need to go down. And this is what the training tries to optimize, to bring down all these three losses. And then we see something else which is crucial for this case, which is this MAP50, which is mean average precision 50. And we want this to go up. Okay, so much better than I thought. Here we end with 88, 87. Let's see where we started from. So actually here I cleared the console, but we started from 48% and we ended with the 87 here, 88, 87. So the loss here is definitely lower for all the three losses. And you see here that the class images, here you see images 1056 and 1056, you see here is the validation set, and here the instances are the object detected. Here we have P stands for, I think it's precision, and R it's recall. But yeah, this is pretty much it, and it saves the model here under runs, detect, train, wait, best and last. But this other part is pretty interesting. So here is just a summary. You see here that it's fused, meaning we went from more than 200 layers to 125 layers. Let me know if you want to know why. But basically, there are some layers like that during training. They are made up two layers like convolution convolution and what is called batch norm, and they are fused together. But let's go here, evaluating the model and the classes. So this is interesting, and again, this is the validation set, and we have the ball. The ball has, and you see that the overall is 88, is 0.88, but there are some classes like, for example, the ball, and the ball is quite difficult to get because it's the smallest object to detect. Player, fantastic. Referee also really good, and the ball, yeah, a lower, but still pretty good. I'm now connected with FTP, so I'm connected to the remote box file system, and so if we go inside here, runs, detect, train. So there are many images, many files. So some of them, these are useful to understand how the how the model has been trained. So let's download all this folder. And this is the result of the training. Resize the image. Here it is. So yeah, the train is interesting, but we can't see we just can't focus on the training because this is how the model learned the images. But the problem is that sometimes here are the losses. And you see they go down and it's great, but the thing is, it's really important to see the loss going down also in validation because sometimes there is what is called overfitting. Basically, the model learns really, really well. The training memorizes the training data, so it gives great result with trained data. But when we use the model with another different set that never seen, it performs poorly. So this is why it's really important to see how the model performs on a validation or a test. So here is going on really great. As we saw, the MAP 50 goes almost touches on 90%, and both precision and recall are fine. So let's find out how this model performs. So we're going to take the weights. We're taking this best and use it in one of our live. So I moved the BAST PyTorch file here and renamed it to a YOLO 11N Soccer PyTorch. And here, this is the classic YOLO 11N, the Nano, trained on the Coco dataset. And we need to convert this to an ONNX. And I've also copied here some extracted frames. So yeah, these are extracted frames. We are going to see them how to see how our model performs with these extracted frames from these are screenshots from a YouTube video. So let's take so this is a live book, and you can find this on the YOLO GitHub repository under examples, and this has inside the Python script to convert the model to the PyTorch to ONNX file, and you find also a link below or in the videos list of this channel to see the video where I focus on where I show how this live book works. But so we want to convert the YOLO 11N Soccer the PyTorch to an ONNX. This is a script. I'm not going much into the details, but this creates the same model but ONNX. And now we are going to load the model. But first, we're going to use the one trained on the Coco datasets, because obviously it's going to detect the people, which like player, but let's see. So for example, let's see this image. So yeah, I expect that it's going to detect all these players, and yeah, let's see what happens. Yeah, so it actually works pretty well. Let's consider it's a nano, and that the image, here we see that the image is 9020 by 1080, but the image is resized to a 640 by 640. So even this person with that resized image, it's a dot. So it's able to recognize the persons, but the thing is, it's not just recognizes the players and referees, it's also recognizing the I don't know, this is not a person, doesn't look like a person, but it's recognizing also people outside. So yeah, this is why, one of the reasons why we need a fine-tuned model. And let's see how our model performs. So let's load with the same image. Let's load our model. We see the classes here. Great, and let's see. So actually here the probability threshold I wanted to 0.3, but yeah, you can tune it and play with it. The first cool thing we see is that it doesn't detect players outside here. It detects the goalkeeper. Let's zoom. I don't know if you can see it, but yeah, here the label is goalkeeper. And yeah, I mean, I've chosen terrible colors, white on yellow and white on light green. But here you can see players and referee, and also this one is detected as a referee, so obviously here is a mistake. Let's zoom out a little bit, but let's try 49, I think. Yeah, you see, goalkeeper. I want to see if 0.1, no, yeah, player and goalkeeper. Yeah, you can use the probability threshold to obviously to play with what you see here, and it works pretty well. I want to find out. You see here, ball. So it's able to find the ball. And again, consider that these images resize to a much smaller image. And so the model itself just sees a much smaller image, and this ball is like a dot. So it's pretty cool what we did so far with just a training set. We found online an open source training set, and we have great results. So this is it for this video. You'll find all the links in the description below. I've put the links of the Coco dataset page, the RoboFlow universe, the dataset, etc. So you'll find all that in the description below. And please try this out. Try to fine tune with some data sets and let me know, because this is what I really wanted to bring with this library. I mean, with the Elixir YOLO library, to be able to use these custom models. I think this is pretty cool. And the next step, obviously, as I said in also the other videos, the goal is to be able to bring tracking. I'll make probably another video about fine-tuning, but fine-tuning something different, plates and dual CR on the, so stay tuned. This is scanning. But then, once we are able to detect plates, or even this case where we have a feed, a stream from a broadcast of a match, of a soccer match, we want to track the objects. So tracking is crucial because we want to identify who are the players, the path of the players, the path of the ball, and tracking in this case, or also in the automotive, like car detection, and the tracking becomes really important. So yeah, stay tuned. Bye.